Imagine you're holding a 3D object and you want to explain it using a single picture. Some angles are useless, right? Like you lose the handle or the spout or the details that matter. But when you have the right angle, one shot tells the whole story. In this video, we'll demystify principal component analysis in 3 steps. First, we'll build the geometric intuition behind the best angles. Second, we'll look under the hood at the math that makes this work. And finally, we'll cover the practical trade-offs you need to know before applying it to your own models. Welcome to Schovia, where we make AI concepts feel like everyday ideas. Take a look at this 3D cloud of points. Each dot is an example, and each axis, x1, x2, and x3, is a feature. Blue dots belong to class A, and orange to class B. And your eventual goal might be to design a model that is able to classify these points, which we'll get to in a little bit. We want to simplify this data because fewer dimensions means faster models, lower storage costs, and a much easier way for us to visualize the patterns. Before jumping into PCA, let's look at what you could do if you wanted to convert this 3-dimensional data into 2 dimensions. You could simply say, I'll drop the x-axis or the y-axis or the z-axis, and in each case, your data would look different in 2 dimensions. You'd lose a lot of information about the data. Just dropping an axis may not be the best way to do this. This is where PCA comes in. It does 2 simple things. It rotates the coordinate system to find the directions that capture the most variation in the data. It projects onto the top directions, which is the same as dropping an axis, the one that results in preserving most of the information. So PCA isn't throwing away information randomly. It's choosing the most informative viewpoint first and then compressing it. Here's why the variance part of this matters. If your point cloud stretches strongly in one direction, that direction contains a lot of information about the differences in the dataset, the thing that makes the examples distinct. A direction with almost no spread, that's often just measurement noise or redundancy, or a feature that barely changes across samples. So PCA asks which direction makes the shadow of the data as spread out as possible. And that becomes the principal component 1. Then it asks again, but with a constraint that what's the next best direction that's orthogonal to the first one. And that becomes principal component 2 and so on. A very important thing to note here is that PCA is unsupervised, which means it does not look at the class labels. It doesn't try to separate the blue and the orange or anything like that. It only tries to represent the overall geometry of the data efficiently. So if the classes become more separable after PCA, that means that the separation was always there in the data. It was just not very well aligned with the original axis. Now that we have the vision, how does a computer actually find these directions? This brings us to step 2, the math under the hood. If you love math, here's a clean version. If you don't, you can just ignore the next 20 seconds and the story is not going to break. PCA starts by centering the data, which means that you subtract the mean value. And then it looks at the covariance matrix, which is a compact summary of how the features are varying together. From that matrix, PCA extracts 2 things, the eigenvectors and the eigenvalues. Eigenvectors are the directions of this rotated coordinate system, eigenvalues are the corresponding things that tell us how much variance lives in each direction. The biggest eigenvalue gives the first principal component. Let's call it PC1. And the next biggest eigenvalue gives you PC2 and so on. PCA finds the best directions to look from ranked by how much structure they are capturing. Once we have those directions, we form the matrix VK containing the top K principal components. So if you want to project it into 2D, then K is just equal to 2. And your projection would look like Z equals to X times V2. And that's it. It's the same points, just in new coordinates. You haven't changed the data set. You have just changed the viewpoint. Now look at the two-dimensional representation of this, where you just retain PC1 and PC2. What you'll notice is that compared to 3 dimensions, the 2 dimensions version just feels much more easier to visualize, much more cleaner, and separates really well between the two categories. Not because PCA is a classifier, because it isn't, but because PCA found the plane that preserves the most meaningful variation. And that plane could reveal the class structure sometimes. And you can quantify what PCA kept with the explained variance, which is essentially how much of this dataset's total variation is captured by PC1 and PC2. So PCA is powerful, but it's not magic. In our final step, let's look at some practical rules that tell us what are some of the common pitfalls that you need to keep in mind. When you use PCA, the scale of the features matters. If one feature has huge units, it can dominate PCA. Standardizing features is often the difference between having an insight and nonsense. PCA is also not guaranteed to separate classes. Sometimes it helps a lot and sometimes it doesn't, because it optimizes variance, not your class labels. If you want a good separation, that's a supervised story like LDA, which is a completely different kind of tool. So PCA essentially shines when your data has linear relationships and some redundancy. Think of 1,000 measurements from a sensor. If many of these measurements move together, PCA finds the underlying independent signal. And when your goal is compression or visualization or denoising or faster downstream models, PCA is one of the most reliable things to consider. Another pitfall of PCA to be aware of is that it's blind to curves. So if your data intrinsically forms nonlinear relationships like a Swiss roll or a spiral, a PCA will always try to force a straight line interpretation. It'll flatten the spiral, making those points that are actually far apart along the curve appear much closer to each other. This loses the true underlying structure. For those curvy datasets, we need other tools like tsne or UMAP. If you want to see PCA in code, we have linked a Python notebook in the description showing the full PCA pipeline and the exact plots that you see in this video. Thanks for joining us on Schovia Labs. Hit that subscribe button for more eye-opening insights, and as always, stay curious.